Hi, Jeff Mucklin here, and this is Science at Home, which is brought to you by the Nurture Nature Center. And this week's video is going to be a real gem because today we're going to be talking about crystals. This is an enchanting spot along the Delaware River where you can find a cliff, this behind me, that is almost made entirely of crystals. It's the old C.K. Williams quarry that I visited back in the radioactivity video. Now specifically, the crystals that we're looking at are mostly mica crystals that form these flat sheets that are piled one on top of the other. And these sheets are acting like little mirrors that bounce the sunlight in every direction. The sun just came out and it looks really nice back here. Mica crystals can be split or cleaved along a common edge without breaking the individual sheets if you're very careful. Now, mica can be ground into a very fine powder, sort of like what we see here, and isn't this absolutely beautiful? Looks like treasure. And this powder has been used in the crafts industry, for example, to make glitter. It's used in cosmetics. It's used in pearlescent soaps to make them look all shimmery. Now, mica crystals, like all crystals, form as remarkably ordered arrangements of individual atoms. Let me show you what I mean. Here I have a couple hundred BBs in a container that can roll around. If I roll the BBs to one side very quickly, they fall into position in a very random way. If we think of this assortment of BBs as acting sort of like an assortment of atoms in a solid, so let's slide the BBs over again. But now this time I'm going to start tapping the container. By tapping the container, I give the BBs an opportunity to vibrate and shift into more stable positions. This isn't too dissimilar from the thermal energy. Any object that's above absolute zero is composed of atoms that are vibrating a little bit. The BBs form a very structured arrangement. You can see rows of BBs. They form nice lines and columns. This is not too dissimilar from the organized arrangement of atoms in a crystal. So here are the BBs just as I left them. And I've been hunting for areas where the BBs are arranged together in nice organized areas. For example, down in here, you can see the BBs are packed very close together. And then there are other regions where there is a gap. For example, along this line right here, you can see a very distinctive gap between the BBs. These are regions where the BBs are aligned, but in different orientations. Let me just draw a line along this region. Sorry, it's right here, actually, right there. And now I'm going to draw lines around the other areas where the BBs seem to lose their alignment. This is a regime where the BBs are aligned very closely together, and this is a different regime where the BBs are aligned closely together. And then this gap area between the two is where the different alignments meet together and cause these misalignments. These funny areas where, if this was a real crystal, where there would be crystal defects. You'll also notice that even within the well-aligned areas, there are gaps. For example, there should be a BB there, but there's a gap. These gaps are able to sort of shift around within the crystal, and they can carry charge, and it's part of the reason why electricity can flow through certain materials. Crystallization occurs when a solid mass of an organized arrangement of atoms forms out of a liquid. We call this precipitation. Some months ago, I did a video where I dissolved some ammonium nitrate salts in water, and the salt appeared to disappear within the water as it dissolved within the water. But I left that container sitting out in my room for many months, and the water has completely evaporated away, and the ammonium nitrate crystals have precipitated back into their solid crystalline form. Another way that crystals can form is if we have a liquid with some material dissolved in it that's changing temperature. A warm liquid can hold more material dissolved within it. If we take that liquid and we cool it down, then some of the material that was dissolved in it when it was warmer is no longer able to stay dissolved within that liquid, and so it precipitates out. Here I have a storm glass, and it contains a mix of crystallizable salts. So I had the weather glass sitting in a bath of warm water for over an hour, and the crystals have entirely dissolved. They're completely gone. This looks like just a clear liquid. Now, if I let this sit and cool off again, the crystals will precipitate out of this liquid and they will form these lovely, beautiful structures within the glass. Crystals are all around us, sometimes in very surprising places. If you have a glass of water with some ice cubes floating in it, that is technically a crystal. Ice is a crystal. When we look at the beautiful structure of a snowflake, we can tell that we're looking at a crystal, can't we? That kind of ordered arrangement, it's indicative of a crystal. Ice is the most common mineral on Earth. Technically, if ice forms outside in a natural setting, that is technically a mineral. It's a crystalline mineral. If you look at granular sugar, it's such a fine powder oftentimes that you can't tell that it's actually little tiny crystals. But if you say take some sugar and dissolve it in water, and then you allow that water to cool down, the sugar will precipitate out and form very large crystals. And in fact, this is how rock candy is made. Rock candy is just sugar that's really showing off its crystalline structure. And if you look very closely, these are definitely not squares. They are a bunch of hexagons merged together to form this very complicated crystalline structure. But salt, in some cases, actually is mined from the earth. It is a crystalline mineral that we get from the earth. Here is a beautiful example of some Himalayan pink salt. Some people like to put light bulbs inside of these and make them into lamps. But this mineral, a vital nutrient in your body, you have to ingest salt to maintain a healthy diet. Quartz is silicon dioxide. That means there's silicon and oxygen atoms in here. The crystals are arranged in a hexagonal structure, and this large piece of quartz is an enormous hexagon. I also have here a piece of amethyst. Amethyst is chemically almost identical to quartz, except there's a few places in the crystal lattice where other elements have been substituted. In particular, iron is often found in amethyst, and that gives it this purple color instead of being clear. Another thing we can look at would be pyrite. This is also known as fool's gold. It looks like gold. It's shiny and a similar color, but it's definitely not gold. It's not even a metal. Pyrite is made of iron sulfide. And then finally, I have graphite, which forms incredibly thin sheets of flat crystal, kind of like mica. But these sheets are so flat and thin that you can't see the individual sheets. But when you rub graphite on a surface like paper, the sheets break off and leave a visible trail, which is why we use these for pencils. We use graphite in pencils. By the way, graphite and diamond are both pure carbon. The same atoms are in graphite as in diamond, the exact same atoms. The only difference is that in the graphite, the atoms are arranged in flat sheets, and in diamond, the carbon atoms are arranged in a cubic formation. So if you've enjoyed this, here's a fun at-home activity that you can do. You can get one of these instant crystallization kits. Basically, what they do is they have a packet, they have a bunch of packets of sodium acetate. That's this right here. These are crystals. And you're supposed to take the sodium acetate and mix it with a tiny amount of hot water. The sodium acetate is dissolved in these 2 cups of water. The crystals are just begging to come out of solution in these 2 cups, but they need a little bit of help. They need a single seed crystal. Okay? If I drop one of these crystals into this cup, it should crystallize almost instantly before our eyes. Whoa, look at that. It's completely solidified in what, just a few seconds. All right, that was pretty cool. Let's try one more experiment. I have a sodium acetate crystal on this petri dish. Let's see what happens if we pour this remaining dissolved sodium acetate onto that crystal. Let's see what happens. Whoa, look at that. It's actually solidifying and crystallizing as soon as the liquid hits the crystal. Wow, look at that. I'm like building an instant stalactite. I hope you enjoyed this experiment. I hope you enjoyed this video, and I hope you enjoyed learning about crystals with me. Thank you, and see you next time.